Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Abdul Aziz and I am from Hasanuddin University. And today I will presenting my science project that was entitled by ODE and polytropic model, solution to calculating the pressure inside the sun with non-homogeneous mass and non-uniform density. It cannot be denied that mathematics is a world language. Mathematics is a science that can be applied in various areas of life, and one field that implements mathematics is astronomy. Astronomy is a field that studies objects and phenomena that occur outside the Earth's atmosphere. There are many branches of astronomy such as astrophysics and cosmology, but the branch I take as an example is stellar structure. Stars are giant balls of gas that are very hot and shine due to nuclear reactions that occur in their cores. Stars have various parameters that can explain themselves. Often, stars, which are the main celestial objects in astronomy, are associated with a fixed state without a change. But however, basically, the parameters inside the stars such as mass, density, and pressure are not constant. Based on this, I had the idea to derive a formula that can calculate the total pressure of a star under condition of inhomogeneous mass and non-uniform density using calculus and differential equation. But before we continue the discussion to higher level, I will first introduce and provide example related to differential equation. What is differential equation? A differential equation is a mathematical equation that relates a function with its derivative. Differential equation describe the relationship between the rates of change of quantities and the quantities themselves. There are many types of differential equation, and one of them is a separable differential equation, which is a type of ordinary differential equation or ODE in which the variables can be separated on opposite sides of the equation. This allows for the equation to be solved by integrating both sides separately. Now, the separable differential equation has a general form like this. For the example, consider the differential equation like this. If we're manipulating the form and integrating both sides, we will have y squared over 2 is equal to x cubed over 3 plus c. And manipulating this, we will have y is equal to plus minus square root of 2 x cubed over 3 plus c accent, where c accent is the integrating constant. Now, we back to the main problem. How to calculate the pressure inside the stars with non-homogeneous mass and non-homogeneous density. There are several steps we must take, and the step is like this. So we move to the first step, the Lens-Emden equation and polytropic models for the sun. Just like what I said before, in reality, stars do not have uniform density. Instead, their density generally decreases from the center to the surface. The Lens-Emden equation is directly related to the modeling of stars with non-uniform density distribution. So, the Lens-Emden equation take a form like this. If the solution of the equation was theta to the power of n as a function of xi, then the density distribution within the star is given by like this. Now, for the stars like the sun, the n value is equal to 3. But the solution of Lens-Emden equation for n is equal to 3 cannot be solved analytically. We have to use programming and numerical methods to get the solution. But however, because we want an analytical solution, we will use the polytropic model to solve it analytically. And the density formula for polytropic model with index n is equal to like this. And for n is equal to 3, the formula will become rho as a function of r is equal to rho c times 1 minus r squared over r squared to the power of 3, where rho c is center density, r is distance from the core, and r is star radius. Now the second step. Before carrying out further calculation, there are several conditions that we must agree on together. That is boundary condition. The first one, the density on the surface of stars is equal to 0 and reaches maximum at the center. The second one, the pressure on the surface of the stars is also equal to 0 and reach its maximum at the center. We move into the next step, deriving the hydrostatic equilibrium equation. Now, take a look at the picture. Consider a cylindrical volume element at the distance of r from the center of the star. The volume element denoted by the black thing in the picture. Its volume is dV is equal to dA dr, where dA is mass and dr is height. Its mass is equal to dA equal to rho dA dr, where rho is equal to rho r as a function of r is the star density at the radius r. If the mass inside the radius r is mr, using Newton's law of gravity, we have this. dFg is equal to negative gmr times rho over r squared dA dr. If we take a look again, if the pressure at the lower surface is P and its upper surface is P plus dP, the net force of pressure action on the element is this. So we have two forces that taking action on the element, that is dFg and dFp. Now, since we want an equilibrium condition, then the total force acting on the element should be 0. So we have to set dFg plus dFp is equal to 0. And if we do this, we will have the equation 2, which is dP over dr is equal to negative gmr times rho over r squared. This is a form of separable differential equation. The equation 2 is also the equation of hydrostatic equilibrium. Now, the next step, deriving the mass continuity equation. So, take a look again at the picture. Consider a spherical shell of thickness dr at the distance r from the center. Now, we have its mass is dmr is equal to 4 pi times r squared times rho times dr. Or, we have another form of separable differential equation like this. dmr over dr is equal to 4 pi r squared times rho. The equation 3, that is the mass continuity equation. Now, for the last step, deriving a formula to calculate the pressure inside the stars like sun with non-uniform density. We already have the density formula for the stars like the sun from the equation 1. If we expanding the 1 minus r squared over r squared to the power of 3, we will have this. And substituting back to the formula, we will have this. It's pretty clear. Now, this form is a separable differential equation if we substitute that to the mass continuity equation, and we will have this form. If we integrating both sides, dmr, integrating from 0 to mr, and integrating the right side from 0 to r, we will have the mass function depending on r. So if we take a look at the final form, we already have the mass equation depending on r. This shows that the mass is also not homogeneous. Now, let's take a look on the hydrostatic equilibrium equation, like this, right? Now, remember that rho as a function of r is equal to m, or mass, as a function of r over v. If we assume that the star is perfectly spherical, we will have this form. Inserting this to the equation, then we will have this. Pretty clear? Inserting the mass equation, we will have this. This is another of separable differential equation. If we do this, we have the form like this. And remember, the boundary condition tell us that P is equal to 0 when R is equal to R, and P is equal to center pressure when R is 0. So, using this boundary condition, we have the formula like this. Integrating the left side from P to 0, integrating right side from 0 to R, and doing some algebraic manipulating, we will have the final form of P, where P is the total pressure inside the star. That is only depending on rho c and R, where P is the pressure of sun, the pressure of the stars, and rho c center density, R star radius, and G is gravitational constant. That is my presentation. Thank you, everyone.